Hello everyone. I'm going to show you the global sensitivity analysis on bistable energy harvest. I'm João Pedro. I'm a master's student in mechanical engineering at São Paulo State University. America is my advisor, Samuel, and Paulo is my co-advisor. Energy harvesting becomes a smart solution in the engineering field and consists in harvesting energy from new activity or environment to convert it into electricity to feed operation some electronic device. Here in this picture, we have some examples of the energy available in the environment, some techniques of conversion, and some electronic devices with low consumption. And in my studies, I concentrate in the vibration energy harvest. That is objective is identify the most sensitive parameters of the stable energy harvest that I considering I input one certain data, and we analyze first for linear electromechanical coupling and second nonlinear electromechanical coupling. I divide my presentation in four sections. First, I introduce some concepts about sensitivity analysis. Second, I present the bistable linear electromechanical coupling in our numerical results. Then, I consider a nonlinear electromechanical coupling, and after, the final remarks. Sensitivity analysis is a powerful tool in statistics, and we can provide a great important information about our model. As we can understand how an input to uncertain data can contribute to the system response, to change the system response. We can find the most important parameter, which is most affect our response. And we can analyze a multidimensional space as in a global sensitivity analysis. It's very suitable for nonlinear studies. We can understand the sensitivity analysis is this flowchart, and we can provide a great information has simplify our probabilistic model construction because we just use the parameters of most influence to our probabilistic model and a non-trivial insight into the behavior of our mechanical system. To compute the sensitivity analysis, I use the variance decomposition, called as Sobel-Winds. We can understand this as the mathematical model, which our scalar output is defined by a model operating function, our vector inputs, that each parameter is defined by a probabilistic distribution. Then we can rewrite this mathematical model using a Hoffman decomposition, that our scalar output is defined by a total mean and sums of the conditional means. And the great property about this decomposition are orthogonality in terms of the conditional means. Then we can define that our variance of the model variance is defined by total variance and sums of the conditional variance in rate of the parameters. Then we can relate this variance in terms of the total variance that is called as Sobel-Winds. That the first order computes the individual effect of each parameter. That's the variance conditional parameter xi in rate of the total variance. This value is 0 to 1. The second order is the Sobel-Winds. The second order of Sobel-Winds computes the joint effect of the two parameters. That is the variance conditional parameter xi and xj in rate of the total variance. Then we analyzing first for the bistable energy harvest, considering a linear electromechanical coupling. That in the left of the frames you have the schematic representation, and in the right the equation of motion that we have in the mechanical domain, the second the electrical domain. Which in mechanical equation have the specific term, a nonlinear potential, electromechanical coupling with linear relationship, excitation conditions. In the electrical domain, we have a lambda has a reciprocal time constant, and the kappa has an electromechanical coupling electrical equation, also have a linear relationship. The quantity of interest is a average power over interval t, described by this equation. Then it's well known that the bistable oscillators have different dynamics behavior. Then we have a low energy orbits, periodic chaotic motion, and periodic motion with high energy orbits. Then we are exploring several scenarios since it have a different dynamic behavior. If here we have the minus Sobel-Winds, which for low amplitude of excitation we have frequency has the most influence. In the middle of the spectrum, which we have the occult behavior, as you can see in the diagram bifurcation. The frequency and the amplitude of excitation is the most influence. And for high amplitude of excitation, we have the couple, the electromechanical coupling in electrical equation, the most influence. Now, in taking account a nonlinear electromechanical coupling, that the piezoelectric coefficient is rate of strain of material, which we can approach our coping with the experimental model described by this system, which puts this in equation of motion, and we have the beta that has nonlinear coefficient coupling in our electromechanical system. Becomes a nonlinear relationship in the coupling. Then we have the results, which we explore in several scenarios for different values betas, which for low beta value, we have almost the system almost the same with the linear electromechanical coupling, but as we increase the beta, we can see a great difference. The beta has a real influence in the individual effect, but it can change other individual and joint effect of other parameters. And it become a nonlinear, non-trivial analysis and complex. Final remarks, we can conclude that in stable regions, we have the kappa is the most important. In the unstable regions, the frequency condition is the most important. The damping has no effect, and the piezoelectric nonlinears have just for high values and change the individual and joint effect of other parameters. The future works include the symmetric potential and comparative experimental model. Thank you very much for the opportunity. Here is my content and acknowledge for the financial support.